Welcome back, everybody, and let me just take in-class attendance very quick. There you go. Good, good. All right, thank you. That's it. All right. So let's just go ahead and get started here today. So first of all, starting with updates. There's no new updates actually, except probably you have to work on project. Okay. This week. Whoa, did you turn in? Not yet. Today is a Tuesday. 1 second. The phase 1A of the course project is due 11 a.m. Did you turn in? Did you? Okay, I hope so. Okay. Hopefully you created some meaningful document. You spent some time trying to do something using the software, and then you came up with the new user interface. Some of the all the interface is kind of replaced with new. You try to come up with the design of a wing and play with it, changing sweep angle and other things. You just play with it. So I hope you went through that. Okay, and then, are you sure? And then this week, Thursday, you're going to turn in phase 1B of the course project. Do you have any objections, or you just do whatever professor says? Okay. Well, if you keep quiet, professor assigns tons of stuff, and then professor usually don't take any argument. Is that correct?
I have a question.
Go ahead.
For 1B.
1B, okay. Let's take a look at 1B. So this is now project 1B. Well, dude, a day and a half from today, well, something like that. Dude, Thursday. Go ahead, question. Let's begin with it.
So the template document says to put the X-foil and the 3D.
Did I say X-foil?
The 2D analysis and the 3D analysis for the wing. I was wondering what kind of content exactly you're looking for the analysis.
Report template. P1B, right? Okay, so this one. Yeah. So let's just go take a look at it. So first of all, the team aircraft baseline criteria, of course, you come up with the size and basic configuration, range, and required performance, stuff like that. Okay. Are you okay with that? And then X-Flyer 5 2D airfoil analysis, which is essentially you're going to pick up your cross-section of a wing called airfoil. It could be a single cross-section, or it could be two cross-sections nicely blending from root to tip. It's called aerodynamic twist. You can do that. Or you can import your own choice of cross-section. It could be someone's design or your own design as a data set. Import into X-Flyer 5 and read up and create the shape. You can do that too. So as a team, you come up with a decision. Okay, team 1, you are our team sacrifice. You do most difficult tasks such as, okay, design your own cross-section, read up and data, blah, blah, blah. Member 2, you probably go like, okay, well, easiest choice, because we're going to go with the easiest choice, the single airfoil and the NACA 4-digit. Just go ahead and do that. But I would count on you because you have to establish a solid database because we're going to use it anyways, Veda kind of member. Member 3, okay, well, it's just to try aerodynamic twist with 2 NACA foils, two 4-digits from root to tip. You can do whatever. In other words, each team member can try, okay, different ways, creating and establishing, this is something called polar mesh, something like that. Mesh, polar mesh, polar design mesh or something. In other words, 2D airfoil data set required for you to design actual 3D wing. Does it make sense? Do you understand what I'm talking about? Well, that's here, okay? Member 1, member 2, member 3. Then based off of those database you build, now you can design your wing. Without it, you cannot do anything. So you need to have certain database of your 2D airfoil. Using that, you can design wing and you can predict performance of the wing.
So that's kind of where my question lies. Like, I understand the task, but what exactly do you want us to put in the document for the analysis? Do you want us to put the data points? Do you want us to describe the airfoil? I mean, what are you looking for?
I don't know. I mean, something useful thing. In other words, of course, I don't want to see like a 25 pages of data points after data points after data points because it's BS. No one looks at it. But suppose if you give me one line, oh, I chose NACA 4412, that's it. That's also another BS because there's no information useful or anything. So basically, starting all the way from here, what is your team's purpose? What kind of airplane you're trying to design? And then as a team, you come up with the best choice, right? You have to come up with the best choice toward the end. So you basically spend some time discuss about what is seems to be the best choice of the design cross-section of airfoil under the category of the airplane we are trying to design to begin with. Then each team try different things and come up with the result. In other words, even though this team is trying to design like a high-end of transonic airplane, you're going to choose NACA 4422. It's like a very thick airfoil. Of course, it's a dumb choice, but why it is a dumb choice, let's find out at this stage. You can do that, of course. So purposefully, you're going to diversify if you have 3 or 4 team members, you're going to purposefully diversify those different choices, compare each other, and then pick up the best results out of your analysis. In other words, what is the typical common airplane design process keep going in senior design today and then like last year? Well, let's choose this because we feel like this is better. Feel like, what do you mean? I want the data. Analysis-based data clearly says this design is the best out of those 4 different choices that our team took. That's what I want to see. That's basically simulation-based design and then design analysis. That's what we want to do in this class, okay? So my answer is very kind of fuzzy. I purposely tried to blow a smoke and saying, I don't know, but I think you know what I'm talking about. Okay. There must be some kind of best presentation, best practice at this stage, driven based on your design purpose, design choice. You want to design this category airplane. I want to make it a best airplane. So in order to do that, let's just, since we have 4 members, let's assign each member a different type of design to begin with. And let's come back later and decide what is the best choice. And then you have whole sets of data analysis behind it. In other words, this design is better because maximum lift to drag ratio is like twice as big. And then if you want to have a cruising condition 0.9 Mach, who's going to choose this part cross-section? I mean, those kind of things can come up with the data using X-5. That's going to revolutionize your design process. Okay, so this summer I'm trying to kind of start up, launch that kind of research group, airplane design, hoping that the Professor Chrysler comes back from Air Force Academy. Or he will, I think. Anyways, so did I answer your question, or am I keep saying blowing smoke and get more confused? I don't know.
More of the second part. I think I get it. Just make a justification for that.
Yeah, that's right. Yeah. So again, lots of things in this project is open-ended. So your team can choose to go in certain direction. I try to, at least, okay. I try to assess and give you a grade based on I don't know what's based on the reasonable decision as a design engineer aero track of Embevero. If your team is not trying to, hey, let's minimize the workload because this class sucks, I don't want to do anything. Let's just do easiest choice. If your team choose to go with, obviously the product is so poor, everybody can see it. This is it's so poor. I mean, or if your team actually came up with certain sets of ideas that you really want to put into practice, Really trying to optimize your design, because design is an art, okay? There's no theory for it. People can actually do awesome design. Some people actually do BS design only. Okay, so this class, we want to address those differences based on the data and analysis theory. That's X5. It has actually revolutionary change of airplane design in a concept. In other words, in the past, only certain people who actually knows a lot of things can do a good job of designing. Because it's an art. You need to know so many small, tiny details, and you need to accumulate experiences and based on. Now, the software actually bypasses all of those things. You can actually do lots of simulation instead of long years of experiences, and then use that data to effectively design a better shape. That's what we're trying to do. Okay. So again, it's very open-ended, but I try to be nice with you. I don't want to flunk you at this stage. You went through Aero, except Jordan, but well, he sort of bypassed that. What's the Aero one? That's the hell. Okay, you bypassed that. By the way, are you gonna be a tutor for Aero? Any one of you? Oh, you want to be?
Yeah. Oh, I'm already hired.
You're hired.
But no one's booking sessions, so I'm not getting any.
Who hired?
Huh?
I don't even know it, because I'm the guy teaching it, and I don't even know you are the tutor.
The
Okay,
tutoring
anyways.
center hired me.
Yeah, okay. So, yeah. So anyways, I'm gonna send you a package.
Okay.
In other words, solutions and other things. Yeah. Okay. Anybody else? You're not gonna do it?
I don't have time.
You don't have time, and you're not interested dealing with those kids. Kind of. So hopefully, David, be patient for so many unreasonable requests saying, I have no clue for this homework, tell me everything.
I won't, don't worry.
You can go ahead, do it, and let them sink in a real exam. They can never solve a problem like that in there. Yeah. Anyways.
I'll help.
I give you all the solutions. So no matter how they approach you, you have a solution. So if the kid doesn't want to think, you can just, hey, this is a solution, go ahead, copy. And then that kid cannot do anything in
I
exam.
don't think I'm allowed to do that.
I'll give you some instructions. Yeah. Okay. So I hope I answered your question. I'm not sure though.
I have a better idea now.
Okay, good. All right. So again, this report is more or less the report for your team. In other words, your team is going to pick up this document and build on top of it. So so 2D airfoil analysis for each team member does different things with a different theme. And then based on that buildup of a data set, you're going to design your wing. And now wing need to come under a certain category. In other words, this is the airplane we want. So based off of that design constraint requirements to begin with, you can only do certain things. However, again, the wing could be radically super, like a swept wing kind of thing, and then find out how terrible in low speed. You can find out so many things, okay, with the radical differences between different members. You can find out, okay, well, let's do really dihedral wing with a huge wingtip and all that, and completely ignoring the manufacturing and all that. But what is the benefit can we get aerodynamically speaking? You can find out those things. And then I guess the best design choices will go down to some very reasonable, okay, well, this is the wing I have seen in the past kind of wing. So there's a reason for it. So let's find out using software and analysis simulation-based design choices. That's quite important. Too bad Jessica cannot do any of those. She's the only one in the design team. So if the design's good, that's good. Design sucks, it just crash and die. Too bad. Anyways. Yeah. Okay.
Can we move it to Tuesday?
Well, you say that so casually. I didn't even notice. What?
There's a lot of work to be done this week.
There's a lot of work. Yes. Everybody has a lot of work. Yes. So you're talking about which one? This one, right? Phase 1B, right? Okay. So phase 1B, let's move it next Tuesday. Suppose if I do that, what happens? Next Tuesday is what? 9th? 9th. 9th. Okay. So you turn in Tuesday project phase 1B and you take the exam on Thursday. Huh? Because the exam is coming up. We can't move exam. So things happen. So as you try to negotiate, postponing, I guess you need to know the cost you need to pay. You're gonna cut into the exam study time, right? Do you still want to go with the Tuesday? Yeah. How about people online? What do you think?
I think extra would be great.
Dan said it's great. Anybody else? Oh, they're quiet. So they're okay.
Matt agrees his mic's broken.
I can hear you. Anybody else? Okay. So project phase 1B, Tuesday, March 9th, 11 a.m. again. All right. By the way, what is the project 1B anyways? Let's just take a look at the document. Let's just take a look at the document. So what do you need to be doing in phase 1B? Of course, you need to come up with the aircraft design baseline criteria, what kind of airplane you want to design and optimize it toward the end of the semester. And you need to go through actually XFlyer 5 tutorials page, and then you need to go through 2D foil analysis and then batch analysis, and then you're going to create the database, and using that database, come up with the very fast design of the main wing. So let's just concentrate only for designing the main wing at this stage. I think that's something you did, right? Last semester, as you took L1, you did the main wing design. She did the design of biplane. And then as you design your main wing, you can actually analyze so many things, such as surface pressure distribution, CP distribution, and then shear force distribution. And also, as you pitch up and pitch down that airplane, what kind of downwash you're going to create. You can even visualize the wingtip vortices and shape and magnitude. And then you can compute parasite drag or induced drag or both accumulated with. And then you can plot lift drag on CL/CD plot, or you can plot the total wing lift coefficient against alpha, CL alpha plot for the wing. You can compute the wing span efficiency. You can come up with how good or how bad your wing to begin with. That's the wing performance calculation. And as you change the design, you can change, of course, the performance. So you can easily change your shape of the main wing, and you can easily calculate and analyze the performance of the main wing. So we are going to actually concentrate on the 3D wing design and analysis at this stage, okay? Now, airplane is more than a wing. That's going to be coming up in phase 2. Okay, so phase 1B, don't go too far. Let's stop here and understand what you can do as long as the 3D wing design is concerned, okay? And then you can actually animate as you pitch up and pitch down the cross section and also entire wing. You can, of course, visualize how the pressure on the surface distributes and how the boundary layers on the surface develops. Where is the transition point from laminar to turbulent? And also, where is the separation point of the boundary layer? Once the boundary layer separates on the surface, the software basically says, I can't converge, I can't converge. Of course, flow is separated. How can you compute something? That's the limit of a panel method. You have to understand this, okay? And in order to simulate the wing performance, of course, your 2D analysis of each cross-section of a wing need to cover the wide enough Reynolds number range so that the wing Reynolds number is not outside of the database. if the wing Reynolds number becomes outside of the data range of your 2D simulation database, it basically spits you out saying, I cannot interpret, I cannot interpret. What do you mean? Because you don't have a data enough to cover that Reynolds number range of your main wing. Okay, so those are some basic stuff you have to cover at this stage. Okay, step by step. You're not going to move on unless you're fully comfortable and understand how the software works and runs. It is closely linked to aerodynamics. Okay, so that's why I'm hesitated to cover the software in Aero 1 because half of the class have no clue about Aero. At that stage, they cannot use this software. Since you went through this Aero 1 class, except Jordan, sorry for that, but you need to kind of catch up. Really steep hill, but you can catch up. Okay, so just to do your best at this stage, step by step, it's basically 2D database plus wing design based off of the 2D database. Okay. All right, then you're going to come up with the report. Okay. Any question here? Okay. All right, so again, it's probably very difficult, but the entire notes of the Aero 1 is posted. So if you want to remember certain things, just go back to Aero notes. Okay, and also this is the YouTube of Aero. Do you have any other question about the project? Okay. All right, so basically going through updates, you're going to, what? Oh, you turned in homework of B1, right? Today's a due date. Okay, so you turned in homework of B1. And then next week, Tuesday, you turn in project P1B. You already turned in P1A, right? And next week, Thursday, is exam 1. Do you have any question about exam? Go ahead.
Sorry, it's a question about the OneDrive. Will there be
Yeah.
specific folders for each phase of the project, or
Yeah.
as I understand it, as the deadline approaches, those folders are going to disappear, right?
Yeah, that's right. That's right. So right now you phase 1. What's your team?
My team is 4.
Team 4. So when the this is Aero, isn't it? So I'm looking at the wrong file. Oh, here we go. So this is phase 1A. So phase 1A file folder, it's going to disappear today. I forgot to do it, 11 o'clock. Sorry for that. It's still there. I don't know why. I can do it now, but yeah, it's okay. So this file folder is gone today. And then I'm going to activate 1B.
Okay.
And then you're going to submit everything in 1B. Okay. And then next Tuesday, this 1B is gone. Yeah, that's right. Any question about the exam? Go ahead.
Well, so it's closed notes and closed books.
Yeah.
Will we memorize the equations?
Equations, I'm trying to integrate within the program statement, or I'll give you equation sheet attached to the program statement, either way. At this stage, I'm not expecting anybody to memorize the equation. But if you don't know what the heck of an equation and you don't know how to use it, too bad, you can't survive. But it's hard to imagine. I mean, it's like a style of my aero class and fluids class, but it's much easier now because you know those things. Okay. So again, you don't have to memorize anything, but I expect you to know how to use it. It's kind of my answer always. And then it's going to freak out aero students always. What do you mean? What's the difference? Well, memorizing means you have no clue. In other words, you met this person, then you're going out this weekend. I have to memorize this person's name because I don't know this person at all. I have to memorize even the name of who that is. I'm going to go out this weekend. Versus, I'm married with this person for 25 years. I know everything. That's a big difference. Knowing and memorizing. And then some people still don't get it. I don't know why. Go ahead.
I was also going to ask, you say only a scientific calculator, but can we use a graphing calculator?
It's a calculator anyways. There's no difference in me.
Okay.
graph, well, calculator that can graph, yes, it's still calculator,
Okay.
yeah. MATLAB is not a calculator, it's a software, an app, you can do lots of things. And MATLAB nowadays, you can even still code up like an aerospace toolbox and do all sorts of things. And then, obviously, this is not the calculator, okay? Please don't claim, hey, this is calculator. No, no, no. This is not. This is a device, which it's going to be more than calculator. No, don't use this as a calculator. So, graphing calculator, do you still have that kind of stuff?
Yeah, well,
Well,
I
you
guess
know.
what I'm asking is, like, this is a scientific.
Yeah.
It's really hard to see what I'm doing.
Yeah.
I
It's,
always use the
well, it's a
source.
still calculator. It's the same
Okay.
thing. Yeah, it's the same thing. Okay. You're not gonna log into the home page and take a look at the solution. You cannot do that, right? So if so,
I don't even know how to graph on
okay,
that.
that's right.
You can download it.
I don't think you can do it with that device. Any other question? Okay. Do you have any question about exam? Like how many problems and how difficult and stuff like that?
That would also be.
You're not gonna derive anything, are you?
Okay. 4 problems. 75 minutes, of course.
Oh, yeah.
It's not, yeah. It's a 75 minutes, 4 problems. Almost all of them come straight out from the notes. In other words, could be example, could be homework, could be something written in the notes, anything. Yeah.
There's no like derive this equation or anything, right?
Could be. If it
wasn't
it could be.
one.
If I emphasized it, in other words, if I emphasize the deriving of equations such as I always do in Arrow, that's going to show up on exam. But did you see any derivation as a heavy extent of details? Probably not, right? In this class. But I think more or less like what is the meaning of this kind of thing? Yeah, that can be. And also read off of the data of a NACO chart. Of course, you did all of those home assignment and you turned in. That could be. If I ask you that kind of question, I need to give you the chart, of course. You have to read off. Okay? Any other question? People online, do you have any question about exam? Good? Okay.
I'm good.
Okay, good. All right, so today we are going to get into Unit B2, and I think I'm going to finish up Unit B2. Now, this is actually fairly important unit because this is going to get right into the project phase 2. So let's just, even before we get into Unit B2, let's just take a sneak preview of a project P2, project phase 2. It's project phase 2. Where? Here, huh? Oh, right here. Project phase 2 coming up right after we complete Unit B3. Okay? So project phase 2, what are we going to do? This is actually now hybrid of X-Flyer 5 / hand calculation and confirmation of how accurate your model and simulation in X-Flyer 5 really is. So this actually is quite important. Unit B2 contents is very, very important because airplane is more than cross-section of a wing, more than just the wing itself. You have to come up with a fuselage, you have to come up with a tail, stabilizing surfaces, and also you need to come up with the controlling surfaces. And then sizing of those will be also very important factor, and how heavy your airplane is, what's the distribution of your weight, where is your center of gravity, where is your neutral point. That's going to account toward how stable your airplane is. So X-Flyer 5 is designed, and then this just to keep evolving into just the total design analysis tool for entire airplane. That's the greatest achievement this software really is. And then this class is designed for it. Okay. So this is the one more step toward the whole aircraft. Here we go. So at this stage, based on your 2D analysis and then your main wing design, your team is going to pick up a baseline design, the best choice out of your team. Now you are going to come up with a configuration of whole airplane. Configuration of whole airplane actually consists of fuselage, cowling, landing gear, tail, whatever, whatnot. You are just going to add all of those things, make it your airplane as an airplane. It's not just a wing flying, no. And then at this moment, without software, you cannot do much, okay? You cannot do much is actually wrong. I'm going to just about start to cover today is if you don't have software, this is what you need to be doing. It's a hand calculation, which no one likes it. Lots of details based on like past experiences and data sets and empirical information, other things. Now, software, the beauty of it is, as you design the whole aircraft, the software actually can predict those things so that you can compare the software results against hand calculation. Now, this hand calculation I'm going to about to cover in Unit B2, B3 is a very classical contents of this class. Dr. Jeff Ashworth and Air Force Academy people spent tons of time developing those contents. Of course, I'm not going to cut it. I'm going to cover it. I'm going to force you to do it anyways. But you have software on your side. So now this is the time you are going to confirm how effective your software really is compared against this theory-based hand calculation. Okay? So that's what you're going to do. So you are going to use the software X55, come up with whole airplane configuration. Now again, if you have 3 team members, each one of those team members can freely come up with your own configuration of your airplane, then you can compare later, come up with the best. So each phase, I'm going to allow each team member to come up with your own unique design. Okay? Except Jessica, sorry, because you are the only one. Okay. So this is X55 whole airplane configuration. Then based off of that, X55 as a software can actually predict the whole airplane performance, how much total lift you can create, how much total drag you're going to expect. Okay, so you're going to come up with that and then compare against hand calculation. So I think this is more or less hand calculation heavy project. So if you have like 3 team members, 2 of them may need to be assigned for hand calculation. One person, well, actually, each member actually come up with a configuration. So each member need to come up with a configuration X55. And then I don't know what you do, but maybe 1 or 2 person do a hand calculation, or all 3 of you do a hand calculation for your own configuration. I don't know. You need to come up with your decision, because it's kind of I'm not like really specifying those details. So please read the document first, and then play with the document. Well, you didn't specify those things. That's what we made a decision. That's fine. This is my first time writing this document, so there must be some loopholes, I know. If you find it, you just go through it. That's okay. All right? But the bottom line is that's my idea. So this is the whole airplane configuration. Each team come up with like multiple choices, and then get back together and then pick up the best. Then move on to the next. Next stage is, of course, you're going to come up with how heavy your airplane is, distribution of the weight and the balance, and then come up with the center of gravity, and then you need to come up with the choice of your propulsion system. That propulsion system gives you the thrust available. So now thrust available, and then your total drag is thrust required. That is going to determine your performance. Okay, so you can basically now determine what's the range of this airplane, what is the endurance of this airplane, what is the takeoff distance, landing distance, stuff like that. And also, if you determine neutral point of the airplane, the last stage is you can come up with how stable this airplane is. You can even simulate the dynamic stability. You are going to perturb in longitudinal direction and short-term, long-term, how long does it take for airplane to come back to the normal situation? If you do a cobra maneuver, how much does it take to go back to the flight? Kind of things. Okay. So that's the phase 4, the final. By the way, phase 4 is a final stage. It's that stage alone is 10%, okay, of the total semester grade. So I'm going to let every team to present your final product. That's going to replace your final exam. So there's no final exam for this class. 2 exams, that's it. So the first exam coming up next week. All right. So having said that, let's just take a look at this. Okay. So this actually covers some details, and then this is the hand calculation. So may not be always accurate. However, if you go through this hand calculation process, and then the number is reasonably matching up against your X-Flyer 5 simulations, that means, hey, you know, from now on, I can use simulations instead. The beauty of that is you can come up with tons of varieties by using simulations, and you can spend simulations before you actually start building fast prototype to be tested. That's probably today's standard for every industry. So you are kind of trained up for that new way or new standard. So you need to be familiar with the simulation method technology that actually requires in-depth understanding of the theoretical aerodynamics. Because this software X-Flyer 5 is a panel method, which is a theory-based, aerodynamics theory-based software. Okay, it's not a computational fluid dynamics and stuff like that, in which I do research for that area too. But this class is based purely on panel method, which is a theoretical aero. Okay, so the beauty of that is if you know more theory, you know how it works, and then you can sort of build a very good model that actually can predict very accurately, and then you do tons of simulations before you even make the first airplane prototype. Okay, that's today's trend, and then if you emphasize that at your job interview, I mean, I can guarantee you get a job. I mean, everybody wants that kind of person. All right. So anyways, let's take a look at whole airplane calculations. Okay. So first of all, we covered lift and drag and pitching moment for 2D airfoil to begin with. We always begin from there. Then using that information to come up with the wing design. Wing design basically gives you the results of wing performance, which is what is the total lift coefficient of the wing, drag coefficient of the wing, and other things. But it's not only that. Third step is you're going to actually set up the whole airplane. Whole airplane comes up with the wing as a main device, but not only the wing. You have to have lots of more things. So usually, a complete aircraft is going to generate more lift. So you have to predict that. Okay. More lift. This is the whole airplane. Because you have more surfaces, including fuselage, okay? Forward surface, such as canard, it could be like a tail surface, you know, horizontal surface, but it could also contribute to the overall lift. So this is whole airplane. Okay? So you have to estimate. So this is the hand calculation-based estimate. So first of all, if you look at the wing, okay, the majority of the lift comes from the wing. And then this is, once again, empirical expression for span efficiency factor by hand. So obviously, if you use X-Flyer 5, depending on your wing configuration and then test condition of simulation, the software actually computes this value, right? Span efficiency. This is actually empirical equation you can also use. So after you design your whole wing, you pick up this equation and compute your own span efficiency factor of your main wing and compare against your X-Flyer 5 result and see how close or how far apart from it. Okay? And then interestingly, this is the function of aspect ratio and then sweep, if you put the sweep. So wing sweep angle comes into play. This is the This is the point of maximum thickness. If you choose to go with conventional design, where is this location? This is quarter code, isn't it? Usually quarter code. So quarter code wing sweep. Now, if you pick your non-conventional cross section, such as, I don't know, NACA 6 series natural laminar flow, or you come up with your own weird shape, this is going to be, again, not necessarily quarter code, but this is a wing sweep. Well, you may not necessarily be putting wing sweep. If you're designing low-speed airplane, that's okay. You can still put the wing sweep on low-speed airplane in which it looks cool, and that's it. Wing sweep doesn't do anything good for your low-speed airplane. Okay, it looks just cool. That's it. Okay. Now, also, you need to come up with an idea of something called absolute angle of attack. This is a kind of new idea, alpha absolute. This is actually angle of attack minus alpha zero lift. This idea comes into play at the stage of your early design. You still don't know what kind of cross-section you're going to choose. So this alpha zero depends on how much camber you have. So if you have no idea for that kind of stuff, you can basically go with absolute angle of attack. Okay? So important thing about that is how much angle of attack you can use, usable. How much usable maximum absolute angle of attack you have. This is going to determine how much lift you can produce. What actually limits for this usable angle of attack? It's actually quite simple. If you take a look at the picture here, the one thing you notice was this is the tip back angle. Tip back angle? I'm not sure. This is tail clearance, usually says. Some of the Air Force Academy surrounds comes into play. Tip back angle. So this is a 15 degrees. And also pilot's view angle is maximum 15. So if you pitch up more than 15, pilots cannot see the ground. So this actually limits the usable maximum angle of attack. Okay? So again, geometry comes into play. Okay? Have you ever seen like an airplane like a GB? Insane airplane. Do I have a picture for that? Let's Google. That airplane, there's one person in GB, yeah, that's right. There we go. GB Model R. Oh my goodness! I mean, you cannot see the ground to begin with. This is one of those airplanes. Okay. Do you want to fly this airplane? Probably not, unless you're crazy. Okay, so again, it depends on your geometry, right? So once you come up with the maximum usable angle of attack, now you can determine CO max. Realistically speaking, your airplane CO max. CO max is quite important because later on, once you have a information of CO max, you can determine stall speed, how slow your airplane can fly. Now, suppose if you augment CO max by using high lift devices, you can even further slow down. So that actually go to what kind of high lift device you need. Suppose if you want to design an airplane like GB, and I want to really slow down that airplane, you need to come up with very weird wing with high lift device. But the wingspan is like this. Wow, I mean, how can I do? Well, let's just do like a double throttle fired for that airplane. No. Again, your design is always trade-off. Okay. Next thing is contribution of high lift devices. This is actually leading edge struts or trailing edge flaps. Okay. Slats and flaps. So usually trailing edge device flaps, if you deploy the flaps, of course, you are going to purposefully increase the usable absolute angle of attack. Let's just skip forward to next page. What does that mean? So this is when flaps, which is trailing edge high lift device is deployed. So this is no flap configuration. This is the absolute angle of attack, right? So this is the max usable. This is alpha equal to 0 at the 0 lift. In other words, this is the alpha absolute. By deploying the flaps, you are going to actually stretch out this much. So this is increased to delta alpha absolute with a flap, okay? So that's what it is. So you can determine how much increase of usable absolute angle of attack by deploying the flaps. You can compute that. This computation depends on what type of flaps you have again. So this is the flap. If you add a flap, you are going to define something called flapped area, which is, this is a shadowed surface right here. This is called flapped area. It's not the surface of the flap itself. We don't usually care about how much surface of the flap you have. You know why? Because over the flap, or the floor is separated. Who cares? Floor is not attached on the flap. So what effectively causes the difference here is the flapped area. So flapped area is quite important, okay? So this flapped area is this. This is called flapped area. Okay? It's not the flap surface area. No, go ahead.
So just checking.
Yeah.
So it's the area not including the flap?
Not including the flap itself, but the flapped area over the wing. Yeah, that's right. Okay. Once again, this is empirical. So somebody find out by using this equation, whoa, you know, if you don't include the flap itself, this is going to work better. Okay. And also, if you have a sweep, you have to have a sweep angle of the flap hinge line. In other words, what is the flap hinge line? This is the flap hinge line sweep. Okay, so you need to include that too. Okay. And then this is going to determine how much you are going to increase your usable absolute angle of attack. Then after you figure that out, now you are going to come up with the maximum usable lift coefficient. Maximum usable lift coefficient for your design. This is quite important because this is going to determine how much lift you are actually going to develop at your maximum usable angle of attack. Okay. Next page. Next page is actually, this comes into play rather later on your stage of your design. That means, suppose if you deploy your high lift devices, it is going to create very strong pitch down moment of your airplane. You have to somehow compensate it because your airplane trying to pitch down always, but you want to fly straight. How would you do that? Usually you're going to use the control surface, typically the tail surface with control surface of the tail is going to counteract and creating pitch up moment that is going to create the rebel flight. This is called trimming. Trimming is quite important. It's going to come up at the stage of performance/stability analysis, trimming. Okay, so this trimming requirement actually is going to affect on your sizing. In other words, how big your control surface needs to be in order to trim for the maximum deployment of high lift devices. High lift devices could be super efficient, in other words, double throated, Fowler, fully stretched up, but that's going to create very strong pitch down moment. So you have to counteract with it. So you need to have a big enough control surface to trim. Okay. in order to compute this, of course, you need a software simulation. Hand calculation can help only certain things. So this is an example. NACA 0006 data basically says that if you deploy 60 degrees split flap, it is going to create 12 degrees increment in alpha zero lift and minus 0.2 increment in CM cortical. In other words, you're going to create pitch down moment at the cortical. You have to counteract with it and then make it trim. So this is going to create how much area you want to have. Assumption is usually, well, this is assumption, okay? A reasonable assumption is that the trimming surface can devote about 10 degrees of deflection to trimming the flap moment, leaving the rest of its deflection angle, it could be 60 degrees, so that means 50 degrees left, using that 50 degrees to control your airplane. So this is the assumption. Of course, you can design in any way you want to, okay? So this 10 degrees comes in, okay? And then this is going to determine maximum moment of trimming required. That is going to lead you into, okay, this is the delta CO maximum trimmable. So this is the maximum trimmable lift coefficient you can compute. So this is a maximum trimmable lift coefficient needs to be added for the CO max trimmable. Okay, so again, this is not the pure aerodynamic. This is actually combined aero plus control surfaces, which is performance / stability, which we're going to cover unit C and D. Don't worry too much about it at this moment. So I guess the beauty is you're going to come up with certain control surface sizing at this stage. It's just a pure guess right now. But later on, as you know more details of your airplane, such as how heavy your airplane is, where is your center of gravity, how big your tail is, and then what is the trimming moment required, that is going to kind of reiterate your sizing process. And then your team realized that, hey, we need a bigger control surface than I thought. Well, you can go ahead and change it to meet this criteria kind of thing later on, okay? So that's actually the beauty of the software, because you can always go back and modify and make it happen, right? Okay. All right. Next page. If you have a canard, which is a forward surface, typically you are going to have a tail, right? Is that right? Conventional, very conservative design, right? If your team goes for very radical design, you can still do it. There's a certain limitation, so let's be careful about that. But if you have a forward surface such as canard, it is going to induce upwash for the main wing. And if you have a tail, which is conventional design, this is going to place inside of the downwash of the main wing. So you are going to compute those things first. And then if you have a leading edge extension such as FA18 Hornet, wing strakes extension, which is F16, okay, you're going to add those areas too. This is going to also contribute to the more of the lift coefficient. Now, important thing is now we're talking about CL alpha. CL alpha is, once again, this is a lift curve slope, okay? You know what it is, right? Lift curve slope is defined such as if you plot lift coefficient CL against alpha angle of attack, assuming this is a linear curve, this is a CL alpha. CL alpha is by definition DCL D alpha, lift curve slope, okay? So obviously, lift curve slope, if you want to have a much higher value, that's better, okay? You keep losing the slope of this lift curve. What is the lift curve slope when you choose a best cross-section of a wing, like a 2D? Oh, this is the best cross-section I have ever seen. What is the lift curve slope, CL alpha? 2 pi is the maximum, yes, that's right, 2 pi per radian. This is theoretical maximum upper limit. 0.11 per degree. You cannot have more than that. It's impossible. So you just keep decreasing this value, starting from 2D airfoil. As you create the 3D wing, this is going to be rest value. If you create entire airplane, this is going to be rest value. But there are some things that actually augment this. One of them is a strike and leading edge extension that actually giving you some favorite effects to increase CL alpha. Okay, favorable effects, I should say. And then, but you have to figure out how much upwash and downwash angle comes into play. It also depends on the shape itself. Again, the beauty of X-5, if you put those surfaces, it is going to, I think it is going to compute that. Okay, all right. So this is a either horizontal tail conventional design or forward surface canard. How much augmentation you can expect, it depends on how much upwash, downwash you have. Okay. So upwash and downwash can be, again, computed based on the empirical equation. This and that. All right. So this is the conclusion. Here we go. So this is the whole airplane's lift curve slope. Like I said, CL is absolute alpha times CL alpha, sorry. Okay. Opposite. CL is equal to CL alpha whole airplane multiplied by absolute usable angle of attack. This is going to predict your whole airplane lift coefficient for a given angle of attack. Obviously, if you use the software X-5, this information can always be easily can get. It actually plots over the range of alpha. Okay, that's something you can get like a snap of finger using X-5. But if you want to do it by hand, this is the process. Okay. Anyways, I know no one likes it, but this is the process. Next thing is drag. Whole airplane drag calculation. This is the pain. Lift is actually easy. Drag is tough, and then drag is probably more important than lift. In other words, if you design a good airplane, that airplane should come with a lower drag. Lower drag means, okay, it is going to be a main driving factor of your airplane performance. Okay, so right now you're seeing this is called whole airplane drag polar plot. This is whole aircraft drag polar. This is important. Okay, why this is important? Oftentimes in airplane performance computation, this is called thrust required. TR. This is how much thrust you need because you have this much drag in order to sustain forward level flight and accelerated, you need this much thrust being provided from your propulsion system. This is called thrust required. This is going to determine your airplane's performance big time in unit C. So as you do a good job at this stage, your airplane is very promising to have a very high performance. Okay. So one of the final goal at this stage using X-5 is come up with this whole plot, whole airplane drag polar. Okay, this is essentially thrust required for your airplane. Okay. Now, important thing is this is the plot you can express using polynomial function. Okay. Important thing is there are two things coming up here. So this is the location. Here's the location. This is called CD0. CD0. This is called parasite or zero lift drag coefficient. The meaning of it is, if your airplane is not producing any lift, how much drag do you have? That's called parasite or zero lift drag coefficient. That comes into play. CD0 right here. And then as your airplane starts producing lift, that lift comes with the penalty of additional drag. It's called induced drag. Okay? Induced drag coefficient. This is essentially drag due to lift. In other words, you're going to create the lift now. That lift comes with the penalty of increased drag. It's called induced drag. So those two added together is a total drag of entire airplane. And then this is going to be expressed in second order polynomial function. Now, important thing here is this is the additional term if your CD0 is not the minimum value of your drag. Because you are interested almost always with what is the minimum drag location. It is actually right here. This is called CL minimum D. So this is the CL of a minimum drag condition, which is 0.3. That is going to be actually minimum drag. Drag minimum right here. It could be a drag minimum right here. It depends on the type of whole airplane configuration. Because those are the very, very important locations you want to have carefully designed to achieve that goal. In other words, you want to shift it, the minimum drag point to here or there. It depends on your design and configuration. Okay. This is going to have later the major impact on your performance. Okay. And then I believe, okay, X5 actually come up with even this equation, which is based on the curve fit of the data. Okay. So you're going to squeeze out this whole airplane drag polar equation to begin with, and then use that equation plotted against actual propulsion you choose. If you choose your propulsion, that is going to provide the thrust available. So how much difference do you have between thrust available to thrust required is going to be your excess thrust. So that is going to determine how much you can climb and you can accelerate and stuff like that. Okay. So this is going to be quite important. All right. So by hand calculation, you can determine those things. This is like a hand calculation-based prediction of CDO, which is parasite drag coefficient. Okay. And then let me just draw a line here. Okay. Interestingly, I'm going to draw a line here. And basically saying anything below that is high speed. High speed. So I'm going to actually kind of argue by myself, but most of you are actually designing low speed airplane. Is that correct? Is there any team trying to design like a really high speed, like a transonic? Please let me know, because there's nothing wrong for that. Nothing wrong for that. You can do that. I guess the high-speed airplane design actually add a few components, mostly hand calculation based, because X5 can only compute up to transonic. X55 cannot do supersonic calculation. I think they probably add that component in the future, but at this moment, they cannot do it. So this is essentially pure hand calculation. So X55 can take care up to transonic. And then beyond supersonic and all that, you're going to add the results based on hand calculation. Okay. And then I keep arguing about this, but suppose if your airplane is purely designed only for low speed, you probably need to do this at the stage of phase 2. In other words, you need to know we are designing low speed airplane, radio control type. Is that right? Yours is radio control type. Suppose if that airplane goes high speed, what kind of error you are going to expect? Let's just do a hand calculation. It's purely imagination. You're not going to do it, but I want to have that just because of the practice sake. Okay? So everybody, every team, no matter what type of airplane, no matter what type of operating range, you have to do this. Suppose if my airplane goes supersonic, how much CD wave am I going to add? This is a computation. What is the critical Mach number of my airplane? By the way, do you guys know P-51D Mustang? That airplane is not designed for supersonic at all, but the critical Mach number is pretty high. That means that airplane, if you put the jet engine, that's going to be darn good airplane anyways for high speed kind of thing. You can argue those things. You can argue. All right? I think the critical Mach number of that body is 0.75 or something. I'm not sure, somebody actually did calculation in the past. That was pretty high as a subsonic World War II airplane. Very sweet design. So you might be curious about it, even though your airplane is just a radio control type, small, tiny airplane. Okay? You can find out how good or how terribly bad your supersonic capability of your designed wing. This is the critical Mach number. And next one is if you put the wing sweep. Does anybody put the wing sweep, by the way? Nobody? You want to? If you put the wing sweep, yes. How much wing sweep actually increase your critical Mach number compared against no swept wing? You can do that kind of stuff. So this is the theoretical based hand calculation of effects of wing sweep. If you put the wing sweep, how much delay you can have for critical Mach number? Okay, you can hand calculate based on the theory. This is not theory, based on the some kind of information in the past. Okay, data curve fit. Drag due to lift. In other words, you need to come up with Oswald's efficiency. Remember, this is a whole airplane. This is much lower number if you compare against the span efficiency of the wing. Okay, remember, wing span efficiency is this is E. This E is going to be lower to E0 for the whole airplane. Okay. So you're going to compute that based on this empirical form of equation. It depends on aspect ratio and also leading edge sweep. This is leading edge because this is high-speed airplane. Leading edge matters. Okay, because the leading edge is where your fast incoming flow usually hits. Okay, so that's why leading edge sweep matters. Okay, next one is effect of camber. If your entire airplane comes with the condition of a heavily cambered type, in other words, this equation, let's just go back a little bit. So if your airplane ended up having this kind of shape, K2 comes in. K2 is not the 0. K2, what is K2? K2 is this term. This term is K2. Okay. So the whole thing is shifted as if you put the camber for your entire airplane. And if your airplane ended up being such a characteristic, you have to hand calculate what is K2. So let's just go down. So that's the K2. Okay. So this is camber effects. Now we are talking about whole airplane, so the camber, it may not necessarily be the right word to choose because camber usually is for airfoil or wing, but this is a whole airplane. So as a whole airplane, you probably have a similar to put the camber on your wing type of effects. If so, you have to figure out the K2. Okay. All right, next one is If you don't have such a thing, you only have K1, of course, right? Oops, 5 more minutes. And for the supersonic flight, you need to have a wave drag added. Okay? So CD0 need to come up with parasite plus wave drag. Do you have this? Yeah, okay, this one. So this is a supersonic region here. Of course, you have a spike of CD0. CD0 becomes parasite plus CD wave. This portion is going to be added right here for supersonic. So you have to predict this added wave drag coefficient. Okay? So this can be done by this empirical form of equation. You need to come up with K1, and then K1 is going to basically add the CD wave into CD0. So CD0 actually spike up at the supersonic region. Okay? And then this one depends on aspect ratio, Mach number, and the leading edge sweep. So if you put the sweep, it makes sense for supersonic airplanes, of course. It is going to delay the critical Mach number. It is going to lower the wave drag coefficients. Okay. Since you are designing low speed airplane, you usually don't put any wing sweep. Okay. So you are going to come up with fairly bad large value of drag coefficient for supersonic region, but you are going to compute that anyways in phase 2. Any question here? This is the end of the unit B2. So next class Thursday, we are going to actually get into unit B3. Unit B3 has actually, this is a master note. You don't have to take any notes in unit B3. 2 subjects on unit B3. I'm going to cover some supersonic pitch up and leading edge design issue and also stealth. Actually, this winter I went to Ohio, Dayton, Ohio. I went to U.S. Air Force Museum with my son. So I took tons of pictures of B2 and also, F-35. So I'm going to share those pictures with you, the stealth airplane. I just took tons of photos up close. So I'm going to cover that stealth, and then engine airframe integration, and the rest of the page. Okay, this is quite important. This one, page 7 to page 11 of unit B3 is the example of whole airplane analysis by hand calculation for F-16. So this is going to be very similar process of a project phase 2, hand calculation. You're going to predict lift and drag of entire airplane. Okay, then you're going to compare against your X-Flyer 5. All right, so we're going to cover that on Thursday. Any question here? Let's stop here today. Any question, people online? Have a good week, and then we're going to see you back on Thursday.
Oh, I have a feeling you can resign.
I know, it's